Hello, and welcome to the Noise Analysis app. This app allows you to compute the root mean square of the current and the power spectral density to evaluate the noise characteristics of your current trace. In order to choose the correct file type, use the File Type drop-down menu. There are three options. Default option is the ABF files, then the Sutter ABF file option, and DAC LabVIEW-based files. If the incorrect file type is chosen, an error will pop up when loading the file. For more information about these file types, please refer to the compatible file type document included with this app. After choosing the correct file type, let's load a file. To do this, click the Load File button. When you load a file, you would see the file attributes getting populated under the main setting and controls. You could see the sampling rate in kilohertz, the current unit. It is always good to verify that the program has picked up the correct units. The trace start, the trace end in seconds, the RMS segment length, and the RMS segments. By default, the program expects to have a minimum of 5,000 data points to compute the RMS, and you would see, depending on the sampling rate, the RMS segment length will vary. The RMS segment is total number of segments from the loaded trace that would be used for the RMS calculation. By default, this is set to 10. The preferred display unit governs the units of the trace displayed during the analysis. By default, it is set to nanoamps. Under QCFA tab, you could see histogram quality control. The kurtosis is useful for traces with more than one channel. For example, the ABF files from the Elements EEDR software has two channels, one for the current, the other one for the voltage. If for some reason the voltage channel is chosen, this section would output a warning based on the kurtosis threshold. The program computes the kurtosis of trace segments, and if it is greater than the kurtosis threshold, an error will be displayed warning the user of excess kurtosis. And in here you can see the data points in each segment used for the RMS calculation. This will be updated based on your RMS segment length. Under File Attributes, you can see all the relevant binary file attributes. This includes the signal channel, the precision of the recording, bytes per reading, data scaling factor, header offset, data channels, endianness, and instrument string. More information about the instrument string can be found in the compatible file type document included with this app. By default, we set the signal channel to 1. By this we expect the current readings to be in the channel number 1. If this is not the case, this should be changed. If you change any of the fields on the file attributes, make sure to click Update File Attributes so that these changes get reflected on the data analysis. The fields under File Attributes, except signal channel and instrument string, others are updated automatically from the header section of ABF files. For DAC files, the program expects a text file containing these fields. More information about how to set this text file can be found in the compatible file type document included with this app. Now, let's go back to the RMS tab. Under Low-Pass Filter Settings, if needed, you could low-pass filter the trace. To low-pass filter the trace, click the Low-Pass Filter Trace Radio button, and this will enable a host of fields as seen. The LPF stands for the low-pass filter. In kilohertz, LPF type drop-down menu allows the user to select the low-pass filter type. There are few options included as seen in the drop-down menu. The filter order is the order of low-pass filtering, which is set to 4 by default. The ripple and the stop band options are only needed for some of the LPF types. The clipping percentage should only be enabled in case there are capacitive structures at the beginning of the trace segment. For example, by default it is set to 5%, meaning the first 5% of the trace segment is disregarded. The low-pass filter setting is also governed by the Nyquist criteria. For example, if you set the LPF to more than half the sampling rate, the program will yield an error when running the RMS calculations. Various binning rules are available under bin settings. There are a total of 5 binning options as seen in the drop-down menu. If you want to manually set the bins, click the Manual Bins Radio button and you can set the number of bins in the total beans field. The seed values are the values that would be used as initial guesses of the Gaussian fitting. By default, auto seeding is enabled. If for some reason these seed values are not suitable, you could enter them manually by clicking the auto seed, which would enable the A, mu, and sigma edit fields, where A stands for the pre-exponential factor, mu is the mean. Sigma is the standard deviation. Once you're satisfied with all the settings for the RMS, you can click the Run RMS button to compute the RMS. We are using a trace with events in this case. Since there are more baseline points compared to event points, the Gaussian fitting is less affected by the presence of the events. However, for proper RMS calculation, it is recommended to use an event-free trace. You can see the progress under the progress percentage field. We saw in real time the current segments that are being used for the analysis, and the histograms and the fits of those segments. If you want to change any of the styling parameters of the RMS plots, click the RMS Styling tab. Under Histogram tab, you can change the axis font size, the grid. The face color is disabled for the default waterfall plot. If you unclick the Waterfall Plot Radio button, the face color and the Use Default colors get enabled. If you want to use your own colors, unselect the Use Default colors and enter the color matrix in the Face Color Matrix field. This is a 3-number input that varies from 0 to 1. Each of the number columns represents red, green, and blue components of the target color. You could also set the face transparency using the face opacity option. For the waterfall plots, you can also change the plot spacing, X-tick spacing, and the view angles of X and Y. If you want pop-up plots, you could click the Pop-up Plots Radio button option. Subplot option becomes available when waterfall plot is deselect. Under the Labels tab, you can set the X, Y, and Z labels of the plots. This takes the standard MATLAB input form. By default, X is the plot number, Y is the delta I in nanoamps, and Z is the counts. You can turn the labels on or off if needed using these radio buttons. And you can also play with the rotation of the labels using these options. Under the Title tab, you can decide whether to include titles or not. If you want the plots to be named sequentially, you could click the Increment option. This option becomes available when Waterfall Plot is deselect. The font size of the title can be set using the Title Font Size field. Under the Limits tab, you can either have the plot limits to be auto, or you could manually set them using the min and max options over here. Under the Fit tab, you can change the attributes corresponding to the fit line. You can change the line width, the plot color. If you want to use your own color matrix, you can deselect the Use Default Colors radio button and enter the color matrix into the Color Matrix field. As before, this is a 3-number input varying from 0 to 1 for the red, green, and blue components of the target color. You can also enter a plot style of your choosing using the plot style. Once you click the Run RMS button, the values will get displayed under the RMS Output tab. You could see the start time, RMS fit, RMS row for each of the trace segments. The RMS fit is based on the Gaussian fitting, and the is equal to the 1 standard deviation. RMS row is based on the RMS function of MATLAB. Using these values in the table, the program outputs the mean and standard deviation of the RMS values for both fit and row values. Using the Export Results button, you can export this entire table as an Excel file. Under the baseline current, the program outputs the mean and the standard deviation of the baseline using each of the segments. If you want to do the power spectral density analysis, click the PSD tab. In here, you can see the sampling rate, the PSD segment length. By default, program expects to have a minimum of 5,000 data points. The PSD segments is enabled if you click the Fit PSD. This is the number of segments you want to use from the trace to do the fitting. If you set this to 10, the program will automatically extract 10 segments from the trace whose length is dictated by the PSD segment length and do the fitting using of the 2 PSD options shown in PSD type drop-down menu. Please ensure that the current unit is properly picked up by the program. Set the appropriate minimum and the maximum frequencies for the PSD analysis using these options. For the fitting, the seed values for each of the noise coefficient can be entered using these options. By default, they're in log scale. If you want the low-pass filter the trace, could click the low-pass filter trace option. The operation of these fields are similar to what we saw in the RMS tab. Once you are satisfied with all the settings, you could click the Run PSD, and you will see the progress in the Progress Percentage tab. Similar to the RMS styling, if you want to change the PSD styling, click the PSD styling. There are few options under the tab's main, title, fitting, and limits. These are similar to what we just discussed in the RMS styling. If you want to change the trace styling, go to the Trace Styling tab and you will see a host of options available for you to change the styling. This includes plot limits, axis labels, plot title, and plot colors and styles. If you want to save the styling preferences, click the Save My Preferences. This will create an Excel file with your preferences. If you want to recall a set of preferences later on, click Load My Preferences. The outputs of the PSD are displayed on the PSD Outputs tab. You can see the segment start time and the log of A1, A2, A3, A4. These are the coefficients of each of the noise components, and more information about this can be found in the SI of the paper, Gateway to Data Visualization and Analysis in Solid-State Nanopores. If you want to export these results, click Export Results. Thank you for watching.